All right, today we are going to kind of tie in our definition of logarithms to this idea that they are the inverse of exponential functions. So today is all about finding inverses. We're also going to have some chance for review during our practice problems. So just want to go into notes right off the bat. We're going to get down a definition, and in this case, we are defining the logarithmic function as the inverse of the exponential function. As simple as that. If we look at this general form of it, there's a log, there's a base, and we're getting our input inside of the logarithm. So we looked at two types of exponential graphs. We looked at a growth graph here where our base was greater than 1. And we looked at a decay graph here where our base was in between 0 and 1. And if you think about what our inverses do, remember that they flip the x and the y. So we are going to kind of mirror across this line of y equals x when we get our inverse graph. So what the logarithmic graph, the inverse of the exponential, looks like is going to be something like this. Hope I'll make that a red line there, sorry. Something like this for that growth graph where it kind of starts, hugs the x or the y-axis, comes up and flattens out. And then for our decay graphs, it is going to kind of look like this, where again we hug that y-axis and kind of move right there. So just some quick exposure on what those graphs look like, and a reminder that they are reflections across that line y equals x. The rest of our work today is going to be dealing with finding inverse functions, and we've actually done this before, so this is kind of a nice review day, plus adding in this idea of logarithms and exponentials being inverse of each other. So for each of these, we're going to have to change our f of x to y, switch x and y in the equation. Those are our two housekeeping steps. Then we go through our steps to solve for y. This is similar steps to what we did when we were solving exponential equations. And finally, just change that last notation step, y to f of negative 1x, just to name it as our inverse. So right away, I'm going to kind of do these first step 1 and step 2, just changing f of x to y. So y equals 6 to the x power. And now I'm going to swap x and y in my equation to just set up the idea that, hey, I am finding the inverse, all right? So now I need to solve for y, isolating it. I have a base, I have an exponent that's equal to something, so I can rewrite that in exponential or in log form. So now I get the log base of 6. My exponent is y, and I have x in the middle there. So there already we have already isolated so that y is by itself. So now I just need to go through and change that y to the f of negative 1. I'm also going to do that step where I kind of write it left to right as well. So my inverse is just the log base 6 of x. Going to add some layers of complexity because you can see in example 2, we have something along with our exponents, so just want to get more practice working with that. And in example 3, you can see that, hey, we don't have that exponential alone. We have this 5 out in front that we're going to need to divide out. So just going to go through my two housekeeping steps first for example 2. Change my f of x to y, so y equals 2 to the x plus 3. And then I'm going to swap x and y in my equation. So x equals 2 to the y plus 3. Now I'm solving for y, getting it all by itself. And I'm going to kind of just highlight this idea that this y plus 3 is my entire exponent. So I have a base of 2. So I'm going to go log base 2. My exponent is y plus 3. And inside my logarithm is going to be that x there. I'll write that in red to just keep that color coding good. You'll notice we don't have y all by itself yet, so we're going to have to subtract 3 from both sides. Just like before, this is going to kind of stay outside the logarithm. Log base 2 of x minus 3 equals y. And we have y by itself now, so we can just change that notation. F of negative 1 equals the log base 2 of x minus 3. All right, this last one is definitely the hardest one we're going to see. We have a 5 multiplying out in front and a 3 multiplying with that exponent. So if we just go through those first two housekeeping steps real quick, y equals 5 times 4 to the 3x, and then switch x and y. So x equals 5 times 4 to the 3y. Now we can't write in logarithmic form yet. First thing we're going to have to do is take care of that 5. So I'm going to divide by 5 on both sides. Divide by 5 on both sides, I get x over 5 equals that base of 4 to the 3y. Now I can rewrite in log form. So I'm going to have the log, my base is 4. Let's kind of go back here, erase that so I have some space. Log base 4 of my exponent is 3y. And inside that logarithm is that entire fraction there, x over 5. Now, lastly, to get y by itself, I need to divide 3 on both sides. One way to do this to make our writing cleaner is I'm going to multiply by 1/3 on both sides instead, which kind of works the same way as it works exactly the same way as dividing by 1/3, or dividing by 3 is multiplying by 1/3. And you're going to see it's going to be a little easier to write if we do it this way. We get 1/3 times the log base 4 of x over 5. A lot of people ran into this last week where we had to take the log and divide all of it. So writing it as a fraction is just kind of another way to look at it. So I'll just change that. My inverse is equal to 1/3 times the log base 4 of x over 5. All right, so we can also work in the other direction. If we're given a log, we can find the inverse by taking the exponential. This is just working backwards from example 1. We're starting with a log function. We're going to find the exponential. That's the inverse. We go through those same housekeeping steps. So y equals log base 6 of x, and then x equals log base 6 of y. Again, we're flipping that x and y to kind of set up our inverse work. Then we're going to solve for y. In this case, we can do it by writing an exponential to get y by itself. So I have a base of 6. My exponent is x, and that equals y. And lastly, changing the y to our inverse name. So our inverse is equal to 6 to the x power. Got 2 more examples here, just kind of seeing some variations. In example 5, there's a number kind of inside our logarithm we're going to have to deal with. In example 6, there's a number outside of our logarithm that we're going to have to deal with. So we're just going to kind of follow the same process and just see what different things we might have to do. So doing my housekeeping here, I got y equals log base 3 of 5x, and I'll rewrite this again. Switching the x and y around, x equals log base 3 of 5y. The logarithm is all by itself, so I can rewrite that in exponential form. My base is 3. My exponent is x, and that is equal to 5y. We can either look at this as dividing by 5 or multiplying by a fraction. I'm going to kind of show it the divide by 5 way, so we can divide by 5 on both sides, and we'll get 3 to the x power over 5. Notice how that exponent is captured underneath the 5 or above the 5 as well. That equals y. And so our inverse there is f of negative 1 to the x equals 3 to the x over 5. All right, lastly, example 6. A couple of things happening here, but let's take care of these blue housekeeping steps. First, we go y equals 4 times log of x minus 2. And we'll switch that x and y around. So x equals 4 times log of y minus 2. Make sure that's a nice minus sign so we can see it nice and clean. Now we're going to try to get y by itself. So I need to move this 2 over first, adding it to both sides. I'll get x plus 2 equals 4 times log of y. And now I'll need to divide that 4 from both sides. So divide by 4, divide by 4. This is going to be a really funky one for sure. We get x plus 2 over 4 equals that log of y. So now I have my log all by itself. There's no base written there, so we know that the base is going to be 10. If you wanted to write that in, you could. We're going to rewrite in exponential form. This one's going to be a weird one. We have a base of 10. Our exponent is x plus 2 over 4, and that is equal to y. Y is all by itself, so now we can just kind of write that naming step there. My inverse is equal to base 10. My exponent is x plus 2 over 4.